Hello and welcome to Alpha Omega training videos. In this video, we are going to investigate the multi-component particle type for Droplets CFD simulation projects using Ansys Fluent software. After that, we will extract the graphical results relevant to different parameters available in the solution. Stay with us. Okay, at first open your Ansys Fluent software from the start menu bar. And after a few moments the Fluent launcher window will be opened. Okay, here we can read our carried out files. I want to read the case file. This is the location of my file. I select it and open. Okay, here I can see the name of my project. Next to the recent files, here we can see the different options. Dimension is 3D. We have a 3-dimensional project. Under the solver options, the double precision is selected. This option is a computational setting that allows for more accurate numerical calculations. This option uses 64 bits to represent numbers compared to the 32 bits used in single precision. Also, we have the parallel processing. Under that, the solver processes, we can specify the number of solver processes. We allocate 12 number of my cores, my hardware to the solution. After that, I hit the start and Ansys Fluent software will be loaded. Okay, the software is loaded. Here this is a graphical window, user window 1. Here's the console, the task page. You can see the options and the case view or the outline view. Okay, first we want to display our geometry by clicking on the display mesh option. Here we can see your boundary conditions, one inlet, outlet and wall boundary condition. Make sure you have enabled the faces, and that's it. Okay, this is the simple geometry of our solution. We can also increase the transparency of the geometry to take a look inside of it. Furthermore, we can enable the as display all, and now we can see the surface elements of the solution. Which, as you can see, it's with the type of polyhedra. You can import your mesh file, and after that, by clicking the make polyhedra, your mesh file will be changed to polyhedra. Okay, we can check our mesh file by clicking on this check option, and here you can see the word done, and make sure that the minimum volume of your mesh file is not a negative value. After that, we can also report the quality of our elements by 2 parameters. The first is minimum orthogonal quality and the second one is maximum aspect ratio. Okay, the orthogonal quality is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to inaccurate results. It's crucial to maintain high orthogonal quality, preferably above zero point 0.1, to ensure accurate and reliable simulations. Also, in case of the aspect ratio refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can handle high aspect ratio cells, but for better accuracy, it's recommended to keep it below 100. Okay, after that, we have the solver options, which the first one is its type, pressure based type solver. The pressure-based solver implemented in Ansys Fluent has been primarily designed to handle incompressible and mildly compressible flows. The underlying methodology of the solver involves using a pressure correction technique to solve Navier-Stokes equations. The solver initiates the process by estimating the pressure field, followed by solving momentum equations to obtain a velocity field. Subsequently, the solver corrects the pressure field by analyzing the divergence of the velocity field. This iterative process continues until a converged solution is obtained. The solver's efficiency and versatility make it an ideal choice for a broad range of flow problems, making it a valuable tool for business and academic institutions alike. Okay, in case of a velocity formulation, our solution is absolute. The time is important in our solution, so we will solve the project transiently, and also the effects of gravity are neglected. Ansys Fluent is a powerful tool for computational fluid dynamics modeling. It offers a wide range of models to simulate different aspects of fluid dynamic problems. For instance, its turbulence models are designed to capture the chaotic motion of fluids. If you're dealing with thermal analysis, Fluent offers that transfer models. Multiphase models, on the other hand, enable you to simulate scenarios where different phases of matter interact. Fluent's combustion models are at your service if you need to simulate combustion. Finally, Fluent's species transport models enable you to simulate scenarios where different chemical species are transported by the fluid. All in all, Fluent's models are designed to help you simulate complex fluid dynamics problems with ease and accuracy. Alright, what we have used in this solution is the energy equation. By double clicking on energy, you can see that this equation is enabled. Hit the OK and close. Then we have the viscose model. In the viscose model, you can see that there is a wide range of options for the turbulence models, from inviscid and laminar model to SAS, DES, and also LES model. Here we have chosen the K omega SST model. The SST-K omega model is a two equation eddy viscosity turbulence model that is widely used in computational fluid dynamics. This model combines the advantages of both the K epsilon used in the free stream and K omega used in the near wall region models, providing a comprehensive and accurate representation of turbulence flow. The SST, or shear stress transport, aspects of the model specifically accounts for the transport of turbulent shear stress, making it particularly effective for flows involving adverse pressure gradients, separation, and recirculation. The model is also highly appreciated for its automatic wall treatment capabilities and robustness in a wide range of applications. Okay, here under the options, there are a few options, and the last one, which is production limiter, is selected. The production limiter is a feature that limits the production of turbulent kinetic energy in the turbulence model. This option is used to prevent the turbulence model from producing unphysical results such as negative values of kinetic energy or divergence of the solution. The production limiter works by reducing the rate of turbulent kinetic energy production when it exceeds a certain threshold, which helps to maintain the stability and accuracy of the simulation. This option is particularly useful in simulations with high turbulence levels or complex geometries where the turbulence model may be prone to producing unphysical results. Okay, now we can close the turbulence model. The next model which is used for the simulation is species. The species transport model is used to simulate mixing and chemical reactions in a fluid. It allows users to define multiple species and their properties, track the distribution of these species in the flow field, and model the effect of a species concentration on the flow. This model is particularly useful in combustion studies, pollutant dispersion, or any application where chemical species interact with each other or with the fluid flow. And here under the models we have the options. In the options, the diffusion energy source is enabled by default. The diffusion energy source is an option that considers the energy source due to diffusion in the energy equation. It is often used when the energy changes due to mass diffusion are significant, such as in combustion process. Here under the mixture material, our mixture is selected: fuel, oil, air. You can go to edit. Here in front of the mixture species, I hit the edit, and here in the right tab, selected species, you can see the materials added to your mixture. You can click on each of them and remove them from your mixture. Make sure that the N2 is your last species. Okay, here you can see that the density is set to incompressible ideal gas. The incompressible ideal gas model is used for low speed flows where density variations are significant. This model calculates density from the ideal gas law but assumes the flow is incompressible. It's useful for simulating natural convection where density changes due to temperature are important but pressure changes aren't significant. Okay, close this window, and that's it. Okay, and close. The next model we have used is discrete phase model. The discrete phase model, or DPM, is a powerful tool used to simulate the flow of discrete particles or droplets in a continuous phase. It's particularly useful in multi-phase flow simulations like particle tracking. Here, the first option is interaction with continuous phase. This option in Ansys Fluent software is a setting that allows users to model the interaction between the primary phase, continuous phase, and the secondary phase, the discrete phase, in a multi-phase flow. This interaction can be um, in the form of drag, lift, virtual mass, wall lubrication, and turbulent dispersion forces. Okay, as our solution is one way, we do not enable the interaction with continuous phase option. After that, we have the tracking parameters, which the first option is maximum number of steps. This option is used to set a limit on the number of steps that a tracked particle can take. This parameter is particularly useful in controlling the combustion time and resources. If a particle's trajectory is complex and requires many steps to compute, it may consume a significant amount of computational resources. By setting a maximum number of steps, you can ensure that the computation completes within a reasonable time, albeit at the risk of truncating the particle's path if it requires more steps than the specific limit. The step length factor. The step length factor is a crucial factor that determines the size of the steps taken by the solver when tracking a particle in the flow field. This parameter is a multiplier for the local cell size, and it is used to calculate the maximum allowable step for a particle. A smaller value results in smaller steps and potentially more accurate tracking, but at the cost of increased computational effort. Conversely, a larger value may lead to faster calculations, but with a risk of decreased accuracy. Okay, the particles will track in an unsteady behavior, and that's it for the discrete phase model window. To define our injections, we could click the injection option. Here you can see that the injection 0 is defined previously. Click on it and set. Okay, in the set injection properties window, first you can enter or specify your injection name, the injection type, which is selected as cone. A cone injection introduces particles into the system from a cone shaped region you specify. You can specify the cone's base center, base radius, and axis direction. And here's the number of streams that will enter the domain from the injection type. Also, under the particle type, we can select massless particle, inert, droplet, combusting, or multi-component. Multi-component particles are composed of more than one material. They can undergo mass transfer with the continuous phase and between the different components of the particle itself. This is used in modeling processes like drying, where a volatile component of the particle evaporates into the continuous phase. Remember, the choice of particle type in DPM depends on the physical phenomena that you are trying to model. Each type has its own assumptions and limitations, and it's important to understand these when setting up and interpreting your simulations. And here, as you can see, the material is selected, the material of the particles. Here the cone type is chosen as solid cone. This type of injection models the fuel as a solid cone. It is typically used when the fuel is injected into the combustion chamber in a solid stream. And finally here you can see that the position of the injection, its diameter, temperature of the particles at the uh, initial time, a start time and a stop time of the injection, And also the other parameters, azimuthal start angle and stop angle, are set here. The direction of injection, the velocity magnitude, and also the cone angle are all defined here. And here you can see their values. Okay, here I click on the OK, close, and close. Okay, that's it for the models. And next we have the materials. Within Ansys Fluent, the materials section offers a robust tool to manage the physical and chemical properties of materials utilized in your simulation. Think of it as a spellbook for wizards brimming with possibilities. This functionality empowers you to effortlessly create, modify, and remove materials, as well as define the characteristics of fluids, solids, and mixtures. It's a valuable resource for anyone seeking to refine their simulation by adjusting the materials employed. Here you can see the fuel, oil, air, materials, species. We have one fluid which is air, the aluminium for the solid, and also the materials of our particles. You can double click on each of these options, and then you can go to the Fluent database, or you can define the materials here by your uh, own. And if you want to go to Fluent database, here you can see the different materials predefined in the software. By clicking them and hit the copy, you will have this material in your project. After the materials, we have the cell zone conditions. Here we have one zone, and we can allocate or assign our materials to the zones. In place of air, we have to select fuel, oil, air into our domain. Then we have the boundary conditions: inlet, interior, outlet, and wall. Okay, I want to classify them based on their type, zone type, and that's a better view. Double click on the window and inlet. The velocity magnitude of the flow is 0.2 meter per second in the inlet boundary condition. In the thermal tab, you can see the temperature. The temperature is 450 Kelvin. In the species, we have specified the volume fraction or mass fraction of the O2, which is 0.22. The other materials have zero mass fraction, so the rest of the mass fraction would be for the last species, which was N2, nitrogen. Okay, then we have the DPM, and in the DPM, the discrete phase boundary condition type is selected as escape. The escape boundary condition allows particles that hit the boundary to escape the computational domain. The trajectories of these particles are terminated, but unlike the trap condition, it is assumed that the particles continue to exist outside the domain. Alright, here I close it. The interior is our zone, and there is nothing to change. In the outlet boundary condition, just make sure that the gauge pressure is set to 0. Other options, leave the other options by default. This is the total temperature of the backflow, if you have any. The species could be 0 for all of them, or you can put the auto to 0.22. And for DPM, it is like the inlet boundary condition, and its type is skip. Apply and close. Okay, the last boundary is wall boundary condition. For this boundary, the wall motion is set to stationary wall. None of the walls are moving, and also the shear condition is set to no slip. In case of thermal condition, the heat flux of this wall is set to 0. In this species, the specified flux is set for all of the materials with the value of 0. And also in the DPM, the discrete phase boundary condition type is set to reflect. In this boundary condition, all particles that hit the boundary are reflected. This is similar to a perfectly elastic collision where the total kinetic energy is conserved. The direction of the particle after the collision is determined by the angle of incidence, similar to a light ray reflecting off a mirror. And close it. We defined all of the options used in the setup section. Close it, and then we will delve into the solution part. Okay, here in the solution section, you can see the different methods used in the project. The pressure velocity coupling is set to simple scheme. The simple scheme is a numerical procedure used for solving the Navier-Stokes equations which describe the motion of fluid. The scheme is iterative and relies on guessing and sequentially correcting the pressure and velocity fields to achieve a converged solution. It's widely used due to its simplicity and efficiency, especially for incompressible and steady state flows. Then we have the flux type, which is selected as distance based, and the discretization methods. Here you can see that the different equations of the solution are selected as first order and also second order append. The first order append method is the simplest and most robust discretization scheme. The second order append method improves upon the first order by using information from two grid points, reducing numerical diffusion and improving accuracy. Okay, also here we have some options which warped phase gradient correction is selected. This option is a method used to improve the accuracy of gradient computation in cells with highly skewed phases. It's particularly beneficial for simulations with complex geometries or high quality mesh. The correction method helps in reducing numerical diffusion and enhancing the solution's accuracy. It's recommended for cases where the default gradient option doesn't provide satisfactory results. In the next part, we have the controls or under relaxation factors. URF is a numerical technique used in iterative methods to control the convergence of the solution. It scales down the computed change of a variable to avoid potential divergence or oscillations in the solution process. Ansys Fluent generally uses a URF range between 0 and 1. If the value is close to 0, the solution will converge slowly, whereas a value close to 1 will converge faster, but this may cause instability if the value is too high. Also, here in the report definitions, users have the ability to generate different kinds of reports such as surface reports, volume reports, force, flux, and mesh, and different or even the DPM report. These reports are capable of incorporating data about the flow field, including but not limited to pressure, velocity, temperature, etc., for the specific boundaries or surfaces of your choice. After that, we have the monitors. In the monitors, you can see the residuals. And here, make sure that the print console and plot options are enabled. Close it. And let's go into the initialization. Initialization in Ansys Fluent defines initial conditions for the computational domain, setting the starting point for the calculation. Standard initialization sets uniform conditions, while hybrid initialization uses potential flow solutions to initialize the flow field, useful when the initial state is not well known. Okay, for this solution, the standard initialization is selected, and these are the parameters used for gauge pressure, velocity in different directions, turbulent parameters, and finally the species. Alright, after you hit the initialize, the solution will be ready to run. Before going to the run calculation, you have the calculation activities. Here, by entering a value, the project will be saved at every time step. So by putting 1, the calculation will be saved after every one time step. The case and data files will be saved. Here are more options. Okay, after defining the autosave, we can go to run calculation, and here we can set the number of time steps, which is 300, and then the time step size, which is 0.001, and the max iteration per time step is set to 1. The Ansys Fluent's iterative mode solves complex problems by dividing them into smaller parts and refining the solution iteratively until reaching the optimal result. It's particularly useful for nonlinear problems and provides better control and monitoring of the solution process. And after that, by clicking on the calculate, the solution will start to run. In the next section, we will investigate the post-processing procedure. Okay, finally, the solution is completed, and here the particles enter the domain and get out from the outlet boundary condition. Alright, we can go to the result section, and here open the graphics. And the important thing for us is the particle tracks. Here you can open it and save display. As there is no particle at the now in the domain, we can go and watch the animation as we define an animation for the solution. And here you can see the animation of the particles. Lower the speed of the animation. And also you can export a video file from your animation by selecting this option, and after that by hitting the right, an animation will be saved into your project location. Here you can see that the particles are entering the domain like a cone and finally escaping from the outlet boundary condition. Alright, you can close this window, and here I want to show you the different results that we have saved for this project. You can choose the different parameters. Here's the hydrogen peroxide water particle diameter. This is the geometry designed in the Space Clim software, and the meshing of the geometry, which is done in the Ansys meshing. Here's the water mass fraction of hydrogen peroxide water mass fraction of H2O in liquid form. And also you can extract the different parameters of the particles. And this animation shows the particle diameter of the hydrogen peroxide water, and how it decreases as it's move along the domain. And this is the particle Nusselt number. Okay, you have various options in the Ansys Fluent software, and you can choose them when you have particles in your domain. Okay, that's it. The simulation is done. We investigated the discrete phase model, species transport, and also the energy equation in our solution. And also here you have a bunch of options to investigate the results of your solution. I hope that you have enjoyed this project.